Oh. How's class going? Yeah. You guys have a worksheet.
Discussion worksheet.
Discussion worksheet, yeah.
Wasn't like that,
Okay.
to be honest.
Cool.
Just surprised.
Yeah. What did you guys talk about in class yesterday?
Yeah, it was
Chain
just
rule.
that weird chain
Okay.
rule thing.
Yeah, that's what I thought. All right, cool. Definitely talk about that. Trying. Oh yeah, I know what I'm trying to do. Okay.
I don't know what anything's been played. I'm like starting. That sounds slow.
You're certainly welcome to eat in here if you want to eat food. It's totally fine with me. Let's see here. Let's get going. Oh, come on, come on. And probably it change form. We have a second, you know, do the whole thing. Those on Zoom, here, you can fill out.
Yeah, I just feel like the one who is like and organic computer has incredible which is sort of like, no, but it's like, and because like this thing is like organic computer, but you have for. So you have a lot of good practice. Yeah. Maybe not aware of the latest providing questions like when we give it Friday, like based on your business practice.
For this class or for chemistry?
This for this one.
Okay.
Yeah.
I probably have some practice material somewhere. To, yeah, yeah. Okay. Pens and pens. All right, I think we're good there. Okay, let's go. Let's talk about the chain rule, which in some sense you already all have an idea of how the chain rule works, right? Like you learned the chain rule in 17A, you do the derivative of the outside function, you do the inside alone, you multiply by the derivative of the inside function. Now we're going to talk about the chain rule for functions of multiple variables. So let's look at an example. Yeah. So let's say we've got the following. This is kind of a wordy example. You probably don't need to write down all the words. I'm going to try to not write down all the words. So let's see what we've got here. So pressure, by the way, if you've ever taken chemistry, you probably know where I'm going to go, or you might, you'll see where I'm going. The pressure P in kilopascals and volume in liters and temperature in kelvins of 1 mole ideal gas are related by the ideal gas law, which is what? PV equals what? Right. N and R are constants. They multiply to approximately 8.31 For the purposes of this, we're not super concerned with the exact numbers. PV equals 8.31 times T. Or PV equals nRT. Cool. So let's set up the following situation. If the temperature of a gas is 300 degrees Kelvin and increasing at 0.1 kelvins per second, and the volume of the gas is 100 liters and decreasing, oh, sorry, no, not decreasing, increasing, still increasing, apologies. Increasing at 0.2 liters per second, how fast is the pressure changing? Okay, well, the idea here is that if you rewrite this equation, we can solve for pressure as a function of temperature and volume. So let's go ahead and do that first. Of course, I always write, it's right too big. I guess that's fine. It's good to write too big so you can actually see what I'm writing. So I'm not going to worry about it. So we can solve our equation PV equal to 8.31 T for pressure and get 8.31 times T over V. Now, thinking ahead to the fact that I'm going to end up differentiating things, I'm going to write this in a way that's a little easier to differentiate. I prefer not to use the quotient rule if I don't have to. I'm going to write this as 8.31 T times V to the minus 1. And here's what I want you to just think about for a second, or notice for a second. If both temperature and volume are increasing, it's unclear if the pressure is going to be increasing or decreasing, right? If the numerator is getting bigger and the denominator is getting bigger, well, maybe one's getting bigger, right? Maybe our value is actually going to get smaller overall. So we don't actually know if this thing's going to get bigger or smaller. We don't know if the pressure is going to be increasing or decreasing. So here's the idea. We're going to map pressure as a function of temperature and volume. But then we also have to note that temperature and volume, and now I know I didn't say this explicitly, but temperature and volume are both functions of what? Right, exactly. We were told in the previous part of the problem that temperature is increasing at 0.1 kilopascals per second, and volume is increasing at 0.2 liters per second. So since those things are both changing as time is changing, they are both dependent on time or functions of time. So exactly, which we'll use a little t for. So here's the path we're going to draw. And this is going to be a picture you're going to draw many times in doing these chain rule things. We have the pressure is a function of both temperature and volume. And then temperature and volume are both functions of the same variable. So whenever you're trying to find the derivative of some higher, like some top level function, the derivative of that with respect to like the lowest level variable. So I'm trying to find how pressure is changing with respect to time. So I want to find the derivative of pressure with respect to time. We have to take all the paths that get us from pressure to time. So we're going to take other color pen. We're going to take this path that goes this way, but we're also going to take this path that goes this way. So to get from pressure to temperature, I take the partial derivative of pressure with respect to temperature, del P del T. And then I multiply that by the derivative of temperature with respect to time, dt dt. And just as a point of note, I said del here because pressure is a function of two different variables, where I said D here because temperature is a function of just time. So as far as this context is concerned, that's why we're writing del's here and T's here. It's not a huge important difference. Like if you mess that part up, it wouldn't be a big deal, but just want to be clear. And then we also have to take the other path. So to get from pressure to time this way, I'm going to find del P del V, derivative of pressure with respect to volume, times dV dt. So you're just trying to find every path that gets you from the top to the bottom. And every time you go, like as you travel on this arrow, you're getting from here to here by taking the derivative of this with respect to that. So we can even write, we don't. And now we're going to find the derivatives. So just to kind of write some things out, if we have pressure equal to that, then if I want to find del P del T, that's pretty straightforward. Del P del T is just going to be the derivative of 8.31 times T times a constant. So the derivative of a function times a constant times my variable T, that's just going to be 8.31 times 1 times V to the negative first. That's it. And we also have that del P del V is a little less nice. Now 8.31 T is my constant. And the derivative of V to the negative first is negative V to the negative second. I don't need to find, well, I could write them down. So looking back at what we wrote down before, dt, that's how temperature is changing with respect to time. We said that temperature was, what did I say? I said it was increasing at a rate of 1, sorry, I said kilopascal, I meant to say Kelvin, I apologize. Temperature is increasing, right? Kilopascal is the measure of pressure. Temperature is increasing at 0.1 kelvins per second. And the volume is increasing at 0.2 liters per second. So if I want to find out what this is, I have to plug all this in here. So I'm going to get that the rate of change of pressure with respect to time is del P del T. So I'm going to plug this in, but I also actually have to, right? I don't want to get a variable when I plug this. I want to actually know the numbers. So I need to plug in what the volume actually was. We look back at what we wrote down. Let's see. What did we say the volume was? The volume was 100 liters. So we're going to plug in 100 liters for the volume and 300 kelvins for the temperature. So doing that, we're going to get, and the numbers are not going to be nice. Don't worry about it. So we're going to get, let's see, del P del T, so it's going to be 8.31 times the volume, which is 100 to the negative 1, times del T, which, sorry, dt, which is 0.1. I'm not going to write all the units until the end, plus del P del V, that's this, and I'm going to plug in the numbers. So it's going to be 8.31 times the temperature, which we said was 300 kelvins, times negative 100 to the negative second power. And then finally, we have to multiply that by dV dt, which is 0.2 liters per second. We could probably make this look, so if I was entering this into a calculator trying to figure out what it was, I would do a little bit of simplifying to make it a tiny bit easier. So I might do something like, say, 8.31 times 0.1 is 0.831, and 100 to the negative first is dividing by 100. That's making things a tiny bit easier. And 8.31 times, I would probably say 300 times 0.2 is 60. So I'd have 8.31 times 60 divided by 100 to the negative second. Well, 100 to the negative second is 100 squared, and it should be a negative somewhere. That makes it just a little easier to plug into a calculator. If we do that, we get approximately negative 0.0415 kilopascals per second. So the idea here is that in this particular situation, if the temperature is 300 kelvins, and if the volume is 100 liters, and if, right, there's a lot of ifs here, and if the temperature is increasing at 0.1 Kelvin per second, and if the volume is increasing at 0.2 liters per second, then we can say that the pressure is decreasing at 0.0415 pascals per second. Or you could also say it's negatively increasing, but that does sound wrong to say. So if you get a negative rate of change, we typically say something is decreasing instead of saying it's negatively increasing. It just sounds kind of weird. Okay, so that's kind of the reason why you might actually do something like this. You might actually have a function of more than two variables, and you want to figure out how it's changing based on how those two inputs are changing. Yeah, so let's look at, so really there questions about what we've done so far. Erica. Exactly, yeah. So I would say that if we're thinking, so in fact, actually, let's look at another example because I think it'll address maybe what you're asking. So let's look at, cool. Let's look at this next example, which is going to be less numbery. It's going to have to be more dysfunctional. So suppose we have the following function, f of xy is x squared times e to the 4y. And we also know that x is a function of t, x is cosine of t, and y is also a function of t, y is sine of t. So, right, you could imagine this is the same kind of situation, right? Both, you could say that my function is pressure, x and y are representing volume and temperature, and then volume and temperature are both functions of time. So x is a function of time and y is a function of time. So same kind of idea. We want to find the derivative of f with respect to time. And there's actually a couple different ways you could do this. First, we're going to do it what's usually considered to be the long way, maybe the harder way, the less nice way. So first, what we're going to do is we're just going to substitute in cosine and sine for x and y. So substitute in x equal to cosine and y equal to sine into the function f of xy equal to x squared e to the 4y. So if we do that, then we're going to have f as a function of time, and we're going to have, instead of x squared, we're going to have cosine squared. Instead of e to the 4y, we're going to have e to the 4 sine of t. And now we're going to take the derivative of that, just like the normal old-fashioned way, where you have a function of one variable, and we're going to differentiate it as usual. It's going to be kind of gross, because it's cosine squared times e to the 4 sine t, but it's totally manageable. The one thing I would say is when you have a trig function to a power, I usually kind of like to, I like to think of it rewritten as cosine of t quantity squared times the rest of the stuff. This just helps me remember how the chain rule is going to work here. So this is like the, what is it, the abbreviated notation here. This is the longer notation here. The longer notation helps me see how to do it. But let's go ahead and do it. So f prime of t. So I've got a product rule here. I see the derivative of this first part is going to be, I've got something squared. So the derivative is going to be 2 times my something to the first power times the derivative of the inside stuff, which is negative sine of t, times the other stuff. So if we're thinking about how the product rule works, right? If we're thinking of this as u and this as v, here's my u prime, here's my v, and then we're going to switch it up. We're going to leave u alone and get cosine of t quantity squared times the derivative of v. So the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And the derivative of that stuff, the derivative of 4 sine of t is 4 cosine of t. Okay, so that's my u times v prime. You can totally simplify this. We don't want to, right? There's no, because we want to see that doing it the other way is going to give us the same result. So here's the other way of getting there. Draw the map. Say, all right, f is a function of x and y, and x and y are both functions of the same variable t. And then we are going to say that df dt, well, again, we're just taking all the paths. So one path to get to t is through x. That's going to be del f del x times dx dt. Plus the other path to get to t is through y, del f del y times dy dt. It's not always going to be exactly like this, but this is the basic idea. It's just every way you can get from the thing you're taking, from the thing you're differentiating, which is the function f, to the variable you're differentiating with respect to, which is the variable t. All right, so now let's take a look. Del f del x, that's just a partial with respect to x. We can do that. The derivative, whoops, you can't see it though. The derivative of x squared times a function of y is just going to be 2x times that same function of y. Right? We're relying back on our partial derivative knowledge that everything that's not x is just being treated like what? Yeah, a constant. And then dx dt, the derivative of cosine of t is negative sine of t. Plus, then we do the other thing. Del f del y, the derivative of this with respect to y is going to be the x squared constant hangs out. The derivative of e to the 4y is e to the 4y times the derivative of 4y, which is 4. And then dy dt, the derivative of sine of t is cosine of t. Now, if you look at these two answers, this answer and this answer, they don't quite look exactly the same. But they are. The only thing that's different is in this second answer, we haven't plugged in cosine for every x and sine for every y. So I'll just point out, for this to look the same as the previous answer, we would need to substitute in, plug in x equal to cosine of t and y equal to sine of t. But then if we did, they would totally be the same, because look, we would have 2 times cosine of t times negative sine of t times e to the 4 sine of t plus cosine of t squared times e to the 4 sine of t times 4 times cosine of t. They're totally the same, just written different. Okay. So I think so. Hopefully, I've kind of forgotten what your question was exactly, Erica. Right. Yes. Exactly. So I would say we didn't do. So I would say we actually didn't do the partial of x with respect to t. We just took the derivative of x with respect to t.
Oh, that's okay. So it's the partial.
Well, so here's why I'm using partial sometimes and derivative sometimes. The reason you use a partial versus a regular derivative is just based on the fact of whether or not your function is a function of multiple variables. So the reason I'm writing here del f del x and here del f del y is because f is a function of 2 variables, right? There's an x and a y in there. On the other hand, the reason I'm writing dx dt and dy dt is because x is a function of just 1 variable, t, and y is a function of just 1 variable, also t. So that's the only reason we're using a partial derivative here versus a regular derivative there, because of the function of multiple variables versus the function of 1 variable situation. In either sense, though, we're still just differentiating, right? When I'm finding del f del x, I'm just saying, okay, well, there's my f, there's my function. Treat y like a constant and differentiate, take the derivative with respect to x like you kind of normally would. Same deal over here for del f del y. Treat x like a constant, differentiate this with respect to y. Yeah. It depends on what they want you to do with it. So you could, the final answer is probably valid either way. And you're probably not wrong, or actually you're right, probably. This is probably the quote unquote better way, because we would like to see that the derivative of f really just does depend only on t. But sometimes people are totally fine with just being like, oh yeah, we can see that if you plug in what you wanted, you would get what you needed. So let's look at a couple more examples because they can be a little more complicated. Let's say we have this function of many variables. Let's say we have W as a function of X, Y, and Z. And X is equal to T squared, Y is equal to 1 minus T, Z is equal to 1 plus 3T. And we want to find, oh, I forgot something. W of X, Y, Z is equal to X times E to the Y over Z. Apologies. Got ahead of myself there. So just like the previous problem, we could totally write W as a function of just T. You could say, we're not going to do that. We're not going to differentiate that, but we could write or say that W of T is T squared times E to the 1 minus T over 1 plus 3T, or X times E to the Y over Z. And then we could differentiate that. But what we're going to do is we say, well, W depends on X, Y, and Z, and all of X, Y, and Z still depend on good old T. And so what I want you all to do for me is write out just the chain rule formula for dW dt. Which you should end up writing out as 3 pieces added together, and each piece, well, I should just say, you should be adding all the paths together, right? Every path from W to T, which there are 3 of, that's what you should be writing down to find this total plus U. Cool, yeah. So when we do this, we're going to get the path through X, which is del W del X times dx dt. The path through Y, which is del W del Y times dy dt. And the path through Z, which is del W del Z times dz dt. If you're not sure what you're writing and you think your professor might care, just try to make it look like you can't tell the difference between your del and your d. That's what I would do. Kind of like try to write the true false thing that looks like a T and an F at the same time, right? I wanted to mention here, it is not a coincidence at all that if you think of these as fractions, like if you think of del W del X times dx dt, if you think of those as fractions, you could think of the del X as canceling out, or the dx is canceling out, and being left with what? Oh, dw over dt. It's not a coincidence. That's how the chain rule in regular, like back in 17a works as well. If you want to, back in time just for a second here, right? If you wanted to find, right, if you had like y equal to f of g of x, you could find dy dx by finding, really you could say it's, I'm gonna write it like this for a second. You don't need to write this part down if you don't want to, because it doesn't look very helpful here. But then we do this weird, so people do this, they make it more complicated than me too. But what they do is they say, okay, I'm gonna let u equal g of x. So then y is really f of u, and the derivative here is really f prime of u times u prime of x. But then we can say, well, f prime of u is really going to be dy du, and u prime of x is really going to be du dx. And the point I just want to make is this notation was chosen with purpose. This was chosen to be so that, oh, it looks like things make sense. It looks like if you think about saying dy over du times du over dx, technically they're not fractions. But so here's what I'd say about these derivatives. They're not fractions, technically, but they act like fractions in almost every way you would want them to. So people often treat them a lot like fractions because things kind of cancel the way you want them to and stuff like that. So even though they're not fractions, they have all the things we want. So you could think of it like, oh, the du here and the du here cancels out, and you get dy over dx, which is exactly what this is on the left hand side. So that notation is nice. It's purposeful. So if things are looking like they wouldn't cancel out the right way to get what you want, then you should be like, oh, I should double check that. So then finding all the things. All right, so let's see. Del w del x. So I've got x times a constant. The derivative is 1 times the constant. And then dx dt is going to be 2t. And then if I want to find del w del y, okay, so now I've got a constant x times e to the, so if I was looking at e to the y over z, I might think of it as e to the y times z to the negative first. So if I'm thinking of y as the variable, then z to the negative first is my constant. And the derivative of e to the something is e to the something times the derivative of the something. Okay, y is the variable, z to the minus first is the constant, so the derivative of y times the constant is just the constant, z to the negative first. And then we have to multiply by dy dt, which is -1. Now, if it's all going to fit over here, all right, be careful. Finally, del w del z is the same kind of thing as del y del z. It's a little bit more challenging though. So we're still going to get the x. We're still going to get e to the stuff. So the derivative of e to the stuff is still e to the stuff times the derivative of the stuff. But now the derivative of that stuff, the y is the constant and the z to the -1 is the variable. So you're going to get y, your constant hanging out, and the derivative of z to the -1 is -z to the -2. Sorry, I'm squishing that all in there. Let me zoom in so you can see a little bit better. Finally, we have to multiply by dz dt. Hey, what's up, Casey? Oh, of course, yeah. So what's del z del t? Sorry, what's dz dt? Cool, yeah. Sorry, I didn't hear you. I think you said it the first time. I didn't hear you. So, all right, just to be super clear here, there's your del w del x. There's your dx dt. You're all confusing. Thank you. There's your del w del y. There's your dy dt. And there's your del w del z and your dz dt. So a lot of the time, when people ask questions like this, they then ask something like, okay, find dw dt evaluated at t equal to, let's not pick something too terrible, James. Sure, let's try t equal to 1. So this is an example of where you don't actually have to write this all as a function of t. You could certainly, if you wanted to, plug in y equals 1 minus t, z equals 1 plus 3t, and x equals t squared for each x, y, and z, but we don't want to do that. You don't want to do that. So here's what we're going to do instead. We're going to say, okay, well, if t equals 1, then we know that x is t squared, so x equals 1. Y is 1 minus t, so y equals 0. And z is 1 plus 3t, so z is going to be 4. That's going to make it a little easier to handle it. So now I'm going to start plugging in t equal to 1. I'm going to get, okay, so let's see, I'm going to get e to the 0 over 4 times 2 times t, which is just t is 1, plus, okay, here's where things are gonna be a little bit less nice. X is 1. I don't really need to write that down. E to the y is still 0, so I get 0 times anything is still 0. 0 times 4 to the negative 1, I guess. Times z to the negative 1, which is again 4 to the negative 1 is negative 1. Plus, now plugging in again, x equals 1, y equals 0, z equals 4. And then y, oh, that's a y is 0. I should just stop writing, right? Because that part there, the rest, I mean, I could plug in the rest and get negative 4 to the negative second times 3, but that 0 there means this whole term is going to equal 0. So don't do more work than you have to. So let's see what we get here. E to the 0 is 1 times 2 plus e to the 0 is 1. 4 to the negative 1 is 1/4 times minus 1. So it looks like we're getting 2 minus 1/4, which is 8/4 minus 1/4, which is 8/4 minus 1/4, which is 7/4, or 1.75. So there's an example of why you wouldn't want to just plug in x, y, and z all equal to within it, because it's easier not to. So do I have one of those examples set up to go? Let me check one thing. I'll hold up for that. Okay. Sorry, there's one thing I just want to make sure that I'm talking about, because I don't think that's cool. I don't think you guys have to deal with that right on. Sure. So if we look at W being, again, it was x times e to the y over z. Or I might prefer x times e to the y times z to the negative first. Let me cover this up here. So if I take the partial of that with respect to y, that's a constant. X is a constant, just going to hang out. And then here's what I'm really thinking. The derivative of e to the stuff is e to the stuff times the derivative of that stuff. But what's the derivative of y times the constant? Right, because again, we're differentiating only with respect to y. So I have like 6 times y. And what's the derivative of 6 times y? Right, so the derivative of this constant times y is just that constant. So we're going to end up getting x times e to the y times z to the negative 1 times just the z to the negative 1. You're welcome. Other questions about this? Okay, let's do one more and then we will, I think we'll move on. But not that one. Oh, we should. Yeah. There's actually not that many. So I'm looking at your next homework assignment. There's not that many of these problems on there, because really what we're going to actually use this for is to do something else. But it's good to practice because you have to do something. So let's do one more. Oh yeah, let's do one more like this. Where'd you go? I had another situation. Yeah, let's look at that. Yeah. Yeah, sure, we can do that. Okay, so let's say we have the following. Let's say we have W equal to, I don't want to make your lives like incredibly awful here. Yeah, let's do this one. Okay. Let's say we have W equal to the inverse tangent of, you guys are like, oh, he did it already. He made it all. I know. I was really debating x plus 2y, where x is equal to s squared times t, and y is equal to s times the natural log of t. So we want to find, well, first we're going to find del W del T. Notice I wrote del instead of D, or del. But the reason I'm writing del here, well, let's actually draw our map. So what is W directly a function of? What variables is W directly depending on? Right. Okay, what variables is x depending on? Right. Right. What variables is y depending on? Also s and t, which is not too terrible. So if I want to find, well, so at the very base level from top to bottom, w is a function of both s and t. So if you wrote this up the long way, which again, I don't recommend, but if you wrote it the long way, you'd have w equal to inverse tangent of s squared times t plus 2 times s natural log of t. So it would definitely be a function of two variables, which is why if I'm trying to find the derivative with respect to t, it is a partial derivative because it depends on two variables or more than one variable. But it's still the same idea. You're still just finding all the paths from the top thing to the bottom thing. So if I'm trying to get from here to here, there are two ways to get there. I can go through x or I can go through y. So del w del t is going to be del w del x times del x del t. That's the path through x plus del w del y times del y del t. The path through y. They are all partial derivatives now because everything depends on more than one variable. W depends on more than one variable. X and y each depend on more than one variable. Quick reminder, so I don't think you're supposed to, or I don't think there's an expectation that you know how to differentiate any other trig function. Sorry, any other inverse trig function, except for inverse tangent. Like I don't think you have to know what the derivative inverse sine is or the derivative inverse secant or any other thing, but there is some level of expectation that you know what the derivative inverse tangent is. So I'm going to remind everybody that if f of x is the inverse tangent of x, or if you prefer, the arc tangent of x, so they're the same thing, just different way of writing them, then the derivative is 1 over 1 plus x squared. Or 1 over x squared plus 1. Either way you want to add those things. So if you haven't noticed already, whenever I'm thinking of the chain rule version of something, I'm just saying stuff instead of x. So when I say the derivative, like the natural log of x is 1 over x, and then I say the derivative, the natural log of stuff is 1 over stuff, right? I'm just replacing the x's with stuff, but then we're always multiplying by the derivative of the stuff because of the chain rule. So if the derivative arctangent of x is 1 over 1 plus x squared, then let me ask you all, what's the derivative of the arctangent of some stuff? Well, it's 1 over 1 plus the stuff. But then what do we have to multiply by? Always. We said stuff, you have to multiply by its derivative because it's the chain rule, right? If you're saying stuff, you're using the chain rule. At least if I'm saying stuff, I'm using. So that's the idea. So if we take the derivative of the arctangent of stuff, we're going to get 1 over 1 plus that stuff squared times the derivative of that stuff. Okay. So derivative inverse tangent with respect to x. So this is my stuff, x plus a constant. And the derivative of inverse tangent of x plus a constant is going to be, hopefully I have enough room here. Let's write it down here. So I find it. So we're going to get 1 over 1 plus our stuff, x plus 2y squared, times the derivative of that stuff. What's the derivative of x plus 2y? Show me on your fingers. What's the derivative of x plus 2y? Yeah, you're right. That's right. This way. Right? Derivative of x is 1, derivative of 2y is 0, because 2y is acting like a constant. So I don't even really want to write the one, but it will. And then del x del t, so looking over x equal to s squared times t, I have s squared, I have a constant s squared times t, and the derivative is the constant times 1. So there's our first piece, plus now del w del y. So now again, the derivative of the inverse tangent of some stuff is once again 1 over 1 plus that stuff squared. But now we multiply by the derivative of the stuff. We're not differentiating with respect to x, we're differentiating with respect to y. So the derivative of our stuff this time is going to be what? Right, it's going to be 2. And then del y del t is the derivative of s natural log of t with respect to t. So the s constant hangs out, and the derivative of the natural log of t is 1 over t. Pretty terrible looking. If I were to simplify this, I mean, I really wouldn't, but if I were going to make this try to look prettier, I would bring stuff in the top of the numerator. So I'd write this first part as s squared over 1 plus x plus 2y quantity squared. And the second part would be, I would write it as 2s over 1 plus x plus 2y squared quantity times t. Again, totally not required at all. Just trying to make it look a little less gross. Okay. And now we're going to do the other thing. We're going to find del w del s. Right? Because there are w has two partial derivatives. It's got the derivative with respect to t and the derivative with respect to s. So let's do that one. Same idea. Now we're going down to from w down to s. And there's still only two ways to get there, through x and through y. So del w del s is going to be del w del x times del x del s plus del w del y times del y del s. The nice thing about this second part is we've already done half of it. We've already found del w del x. It was this. We've already found del w del y. It was this. So we don't have to think about what that is again. We can just copy our work. So I'm going to say, okay, well, great. Del w del x is 1 over 1 plus x plus 2y squared times 1, which I'm not going to write. And then del x del s, the derivative of s squared times a constant is going to be 2s times the constant. Right? S squared is the variable, t is just the constant multiple hanging out. Derivative of s squared is 2s. And then these are a little bit long, right? It's like, okay, we can do it. Del w del y is going to be, again, the same as it ever was. 2 over 1 plus x plus 2y squared, or 1 over 1 plus r stuff squared times 2. And then the derivative of y with respect to t, or the partial derivative with respect to t, is going to be, oh, sorry, not with respect to t, with respect to s, apologies. Del y del s is going to be 1 times natural log of t. And again, no one should be really asking you to like plug in x equal to s squared t and y equal to s natural log of t. I guess they could, but the more likely question is to ask you, great, so what's, for example, yeah, let's go ahead and do that. We can do that. I'm going to try and make it not too terrible. I'm going to try, but it might be hard. Let's see if I can think of something that's not going to be too awful. Let's say we want to say, what is del w del s at the value of, sorry, I'm trying to make this, see, I don't even want, if this too, no, we shouldn't do it. The problem is oh no, I lied, it's totally fine. At your s comma t equal to 1, 1. So let's see what happens. So if s and t are 1, 1, I probably want to know what x and y are both going to be. So we know that x is equal to s squared times t, which is equal to 1 squared times 1, which is 1. And y is equal to s times natural log of t, which is 1 times natural log of 1, which is 0. So if s and t are 1 and 1, sorry, we know that x and y are 1 and 0 respectively. So when I start plugging in here, I'm going to get 1 over 1 plus 0 squared times 2 times s times t. plus the same thing here, 2 over 1 plus 0 squared times the natural log of t, which is 1. So that's not so bad. When we calculate this, natural log of 1 is 0, which means this whole entire term is 0. And we're left with 2 times 1 times 1 over 1 plus 1, which is 1. It's a lot of ones. Worked out nicely. And since we're already here, we might as well do it for the other one as well. So if we want to find out what del W del T is when we plug in 1 comma 1, let's find out. We plug in again S comma T equal to 1 comma 1. We're plugging into, oops, you can't see it. I keep trying to move so you can see everything. So I'm plugging in now to del W del T. I'm going to get 1 squared over 1 plus 0 squared plus 2 times 1 over 1 plus, sorry, 1 plus 0 squared. Oh, I did 1 plus 1 anyway, times t, which is 1. And then we calculate it. We get 1 over 1 plus 1, and we get 2 over 1 plus 1 times 1. So we end up getting 3/2. So that's not a completely unreasonable thing for someone to ask you to do. To find a derivative of a function at some level and then plug in your inputs equal to something. So I would say the key kind of thing to take away here to see that if you have to do this is you don't want to take this and like plug in x equal to s squared t and y equal to s natural log of t for each x and y. What you want to do is just say, oh, if s and t are 1 and 1, figure out what x is, figure out what y is, and then plug in those values for x and y, and plug in the s and t values for s and t. So not too terrible. All right, so I think we don't, yeah. I don't see any of it. Let me just double check one thing. Yeah, question. So good question. So here's what I would say. So if I were to write this out, although, yeah, we can write this out. So if we look back at our original function, I'm going to first point out that if I actually plugged in x equal to that and y equal to that, we could have written w as a function inverse tangent of x, which is s squared times t, plus 2 times y, which is 2 times s times the natural log of t. And so now let me ask you, how many variables is w a function of? 2. And so when we're writing down the derivative of w, we have to say it's a partial derivative because it's not just the full, right? Del w del t isn't the full derivative. It's just part of the derivative, the partial derivative with respect to t. But there's also a partial derivative with respect to, s down there. Similarly, x is a function of how many variables? 2. So I can't write dx dt here because it's not the right thing to write. I have to write del x dt because it's the partial of x with respect to t. And similarly, del x del s here and del y del s here and del y del t there. So really, the only reason you have to write a partial derivative versus a regular derivative is, does that thing depend on more than one variable? If yes, then when you differentiate it, it's always a partial derivative. If no, then it's just a regular derivative. It's a good question. Okay, so let's see. Let me look real quick. Okay, that's the thing. I don't think I will come. Let's double check. Yeah. Yeah, we're good. Okay, cool. So now where are we going? We're going this way. Yeah. We got time. Okay, we got time. So here's what we're moving towards. We're moving towards talking about, in fact, we already have talked about in some sense, directional derivatives. You all already know how to find 2 directional derivatives. The derivative in the direction of x and the derivative in the direction of y. So those are 2 things you already know. But when we talk about directional derivatives, generally, the idea is that we're going to be on some surface, and we're going to pick a point on that surface and then ask you, what's the derivative in that direction, or that direction, or that direction, or any direction? And to do that, we need to recall a few things from before. So, but it's really just say, when you think of a directional derivative, you should imagine yourself on a surface, like on a hill. Pretend you're on like some part of a hill that's not the top, maybe you're right here and you're asking, okay, how steep is it if I go that way? Am I going down? Oh, it's a negative slope. Am I going up towards the top of the hill? It's a positive. But maybe I'm kind of going around in a very normal way to go up a hill, right? Like a switchback, right? Or if you're going like around, so you're not like going up the steepest way possible. The slope in the direction you're traveling is the directional derivative. Just like normal, slope is the derivative. It's just now we're talking about being on a surface and asking, if I move that way, how steeply am I going up or down? Okay, so we're gonna, but before we get there, we have to kind of give ourselves a little bit of buildup here. So let me remind you of a couple things, and you may or may not want to write this all down. It's not all super important, but let me remind you of a few things we learned in 17b. If you have two vectors, say u and v, and there's some angle between them, which we typically call theta, then the dot product of u and v, of the vectors u and v, is u dot v, and it's equal to, well, there's two ways of calculating this. One way of calculating it is finding the length of u times the length of v times cosine of the angle between the two vectors. You can say length, you can say magnitude, either word is fine. So this is just the length of u, and this is just the length of v. And then I will just point out, side note, if u and v happen to be perpendicular, so maybe they look like this, the angle between them is 90 degrees, and their dot product is how much? What's cosine of 90 degrees? That's sine of 90 degrees. Yeah, it's 0, right? If you go, so let me have the unit circle. I know it's been a while for the unit circle, but if you're on the unit circle and you go 90 degrees, you're at the point 0, 1. And 0 is the x coordinate, which is cosine, and 1 is the y coordinate, which is sine. So cosine of 90 degrees is 0. Meaning, if two vectors are perpendicular, then their dot product has to equal 0. Because the angle between them is 90 degrees. Cosine 90 degrees is 0. Doesn't matter how long they are. A number times 0 is still going to be 0. Okay. Another way, so here's the thing. Normally, we don't know what the angle between two vectors are, right? Or it's not easy to find, especially if they're like three-dimensional vectors. And you're like, so there's an easier way to calculate the dot product. So if we know, for example, that u is equal to, has your professor talked about how they're going to write vectors in class? Okay, there's like at least 2 or 3 good ways of writing vectors. You can write them, some people like to write them with these brackety things. Some people like to write them as a times I plus b times j, where I and j are unit vectors in the x and y direction. And some people like to write them as columns, column matrices. These are all perfectly valid ways of writing a vector that's going A in the x direction and B in the y direction. So if I want to draw this vector, just so you all can see what it looks like. Again, I know I haven't picked numbers for A and B. They're constants. So I'm just saying, here's my vector that terminates at the point A comma B, and it's gone A in the x direction. and B in the y direction. That's my vector U. So for example, if I want to draw the vector W equal to, I'm going to write it in the three different ways, just to be super clear. 3, 2, or 3i plus 2j, or as a column vector 3, 2. I would just be going over 3 and up 2. So say, okay, you go 1, 2, 3, 1, 2. And there's my vector W. That's it. We typically, unless there's a reason not to, imagine a vector emanating from the origin. Okay, so if U is equal to this, and V is equal to some other vector, like C comma D, like I said, comedy, not funny though, which is CI plus DJ or CD, then the easier way to calculate the dot product is to multiply their corresponding components together and add the results. So here you could say that U dotted with V is equal to A times C plus B times D, which is much, much better. Or I should say better, I should say easier to calculate. If you know how to write, and you, because usually you're going to be given the vector in this way, where you know the X and the Y component. What did I want to say? Oh, I want to say. I will point out that when you take the dot product of two vectors, you get back a real number. You get back a scalar. You don't get back a vector. You get back just some value. Okay. So, for example, we take these two vectors, U being the vector 1, 4, and V being the vector 5, 2, then the dot product of U and V, or U dot V, is 1 times 5 plus 4 times 2, which is 13. And just to be super extra clear about things, order doesn't matter for the dot product. You can dot product in either direction. So V dotted with U gives you the same thing. It's 5 times 1 plus 2 times 4, which is still 13. Okay. The other thing we need to kind of know to talk about directional derivatives is how to write the parametric equation of a line, which is not as terrible as it sounds. So let's say we've got a line that goes through these 2 points. Goes to the points, sure. 1, 2, and 4, 7. We'll call the line now. So typically, you need 2 points to define a line. So if you're given exactly 2 points, what we do is the following. Pick one of the points to be your quote unquote starting point. Usually doesn't matter. I'm gonna say this is my starting point. I'm gonna start at time equals 0. Because the idea is I'm trying to parameterize this. I'm trying to write both X and Y as depending on some other parameter T. By the way, this might be where you start to see why we've been talking about the chain rule thing we were just talking about. Because what we're going to be doing is we're going to be saying something's depending on X and Y, and both X and Y are depending on this other parameter T. Kind of where we're going with this, why we were doing that. Over here, we're going to say, well, let this be T equal to 1. You can pick anything, but 0 and 1 are the standard choices because they're easy. So then, if we're trying to parameterize. In case that was right, my last name is Parameter, that's why I said that. It wasn't just random. So parameterize a line. What we're going to do is we're going to imagine a particle moving from the point where T equals 0, so from the point 1, 2 to the point 4, 7 at a constant speed. Otherwise, if it wasn't constant, you could make up all kinds of weird functions that would make this work. So I want to write x as a function of t and y as a function of t. Well, I know that when t equals 0, I need x to be 1 and y to be 2. So I need a 1 plus whatever is going to go going on with t, and a 2 plus whatever is going to be going on with t. And then from here to here, well, from t equals 0 to t equals 1, x needs to increase from 1 to 4. So I need 3 more. So I need 3 times t, because t is increasing by 1. And for y, well, in fact, you all should be able to fill in here. Go ahead and fill in what's going to go in. What times t do I have right here? Let's see. We should be getting, show me on your fingers. Yeah, we're going to get 5 times t because we need to go from 2 to 7, which is fine. So let's check this out just to make sure. If you plug in t equal to 0, you get x is 1 plus 0 and y is 2 plus 0, which is the point 1 comma 2. And if you plug in t equal to 1, you get x is 1 plus 3, which is 4, and y is 2 plus 5, which is 7. And then if you kept going in that same direction, right, you could plug in lots more values of t. So like over here, if you plug in t equals 2, you're going to get the point. Let's see, if t equals 2, you're going to get 1 plus 6, comma 2 plus 10. Which makes sense because each time it looks like I'm going essentially over 3 up 5, over 3 up 5, over 3 up 5 the whole time. This is how we write the parametric equation of a line. You just essentially find your initial point, and then you find the difference from your initial point to your next point, and those are the coefficients of t. Great. Also, this kind of makes sense. It's a constant speed because you take the derivative of x and the derivative of y. I'll just tell you, right? dx dt here is just 3, and dy dt here is just 5. So our derivatives are constant, which means our speed is constant. Okay. So now is where, yeah, we have, I keep looking like we have enough time. Okay. Because I want to get to the kind of conclusion of this, so then we can talk about what it all means. So let's look back to our, and I'm just gonna show you this picture instead of trying to draw it because it looks better. So let's remember our mountain, my favorite function of 2 variables, 9 minus x squared minus y squared. It looks like this, and we're looking at the point 1 comma 2 comma 4. And what I want to really ask is, I want to find out what the derivative of, or what the slope of the line would be if I moved in a direction that wasn't just in the x or the y direction. So if we look at the level curve at z equal to 4, right? That's just this blue level curve here, z equal to 4. I want to say, well, what happens if I'm moving in that direction, right? Not purely in the x direction, not purely in the y direction, but essentially in, I don't have a green pen. Do I have a green pen? I have a green pen. Is there any ink in it? It's a real question though. If we're moving in this outward direction this way, there's like no ink. So what I would point out, and this is where right, we're kind of moving in this. If we're moving in the plane, we're kind of moving that way. That's the idea, is that we're saying if I move horizontally this way, out from the surface, what's my slope going that way? Like, right, because I could try to like be on the mountain and walk straight out this way, but I can't because like there's no ground. And so if I try to walk straight out this way, away from the middle, I'm going to be going down. So I'm trying to find what that slope is. Okay, so here's what we're going to do. So I can, yeah. So suppose we are at that point. Let me 1 comma 2 comma 4 on our mountain, hill, mountain, whatever, which is 9 minus x squared minus y squared. And we want to move in the direction of the vector 3/5, 4/5. So here's what we've got. So we're on the circle. Again, the circle that's at the height of 4. And the x coordinate, y coordinate is 1, 2, which sure, looks about like right there. So there's our 1, 2, 4 on the surface. And that's corresponding to why can't I throw away pen? Sorry. And that's corresponding to that spot right there on our surface. So I want to ask, okay, what's going to happen if we move in the direction 3/5, 4/5? So 3/5 in the x direction, 4/5 in the y direction. Ooh, actually, I think I wanted to, sorry, I want to make sure it's not stupidly easy. I think I actually wanted, sorry, I apologize. I think I want to make that 4/5, 3/5. I don't want, if I do it the other way, there might be some weird coincidence that makes things seem nicer than they actually really are in reality. So I don't want to give you a false sense of, oh, this is really not so bad. So sorry about that. So we're going 4/5 in the x direction, 3/5 in the y direction. So we're going more right than we're going. I want to know what happens if we go that way. Okay, so here's what we're gonna do. We're almost there, I promise. We've still got 10 minutes. We're gonna get there. Don't worry. I imagine this is all kind of being like, well, something's gonna happen. We're gonna see something, I promise. So let's go ahead and parameterize this line. So this line that goes through that point, and that's the point in the XY plane. That's just the point 1, 2. I don't care about the Z coordinate. I'm just thinking of the XY plane. And I know that I'm going through the point 1, 2, and then also I'm going through the point that's, well, if this is the vector 4/5, 3/5, then the next point over is 1 plus 4/5 in the x direction and 2 plus 3/5 in the y direction. We probably actually don't need to know that to parameterize it. All we really need to know is that if I want to parameterize it, my x of t needs to be 1 plus 4/5 t, and my y of t needs to be 2 plus 3/5 t. Let's think about that for just one moment. If t is 0, I get the point 1, 2. Great, that's on my line. If t is 1, I get the point 1 plus 4/5, 2 plus 3/5. So this parameterization will always make me go over 4/5 up 3/5, right? And we'll just keep going on that line. All right. So now what we want the slope of this function in that direction. So we want the slope of f of x, y in the direction of the vector v. But here's the thing. So check this out. Look what we've got. F depends on x and y, and x and y both depend on t. So if I want to find the derivative of f in this particular direction, I'm just going to do the derivative of f with respect to t. So we want df dt. Let me see if I can make that a little more clear, because when I remember when I saw this the first time, I was kind of like, this seems, I don't really see why that's true. So let's think about it this way. If we're on this line, if t is getting larger, which way am I going? Am I going straight x direction, straight y direction, down to the left, up and to the right? Which way am I going if t is getting larger and larger and larger? Right, I'm going on the line, right? So that's really important to note. If t is increasing, I am traveling in the direction of that line. Okay, so now I'm asking, how is the function changing? What is the derivative of f as t is increasing? So it really does actually make sense to ask, what is df dt? How is my function changing as t is increasing? Now, here's what we should expect to happen. We should expect it to be negative. Right, we're moving out away from the top of the hill, so we're definitely expecting a negative. Let's see what it actually is. So to find this, I'm going to say, well, let's make our map. F is a function of x and y. X and y are both functions of t. So df dt is going to be del f del x times dx dt plus del f del y times dy dt. All right, so let's see what we've got here. And actually, so before we see what we've got here, I'm going to rewrite this in a different way. So this is equal to the vector del f del x comma del f del y dotted with the vector dx dt comma dy dt. So this is a reminder, right? The dot product of two vectors is just the first components multiplied together plus the second components multiplied together. So this is totally that. Okay. So in this particular case, well, in fact, I really kind of don't want to see what the numbers are, but we're going to see it anyway here. So here's what this is. Del f del x comma del f del y. This is called the gradient of f. I'm gonna write that down here just so we don't forget it. So the gradient of f is a vector, and it is always upside down triangle with an arrow over it, f, and it's always equal to all the partial derivatives taken in order. So typically, if you're thinking of f as a function of x and y, which is almost always what we're doing in this class, the gradient is just del f del x comma del f del y. But if you were in another class and thinking of f as a function of, say, 3 variables, if f was a function of x, y, and z, then the gradient would be the vector del f del x comma del f del y comma del f del z. So it's all the partials in the order that makes sense for that. And then I will also point out dx dt is just, well, the derivative of this with respect to t is just 4/5. dy dt is just 3/5. But that is just our vector v that we were moving in the direction of in the first place, right? If we look back here, right, we were moving in the direction of that vector, which was, from here to there. We went that much, 4/5 over, 3/5 up. So really what we've got here, and this is what I want you to really see, this is kind of the big result, is that the derivative of this function f in the direction of the vector v is equal to the gradient of f dotted with the vector v. That's the directional derivative. Kind of super cool. There's a couple things to say about this. Well, first, let's actually calculate it for this particular problem, right? Like, it's nice to see the theory. Oh, what time is it? Got time. Okay, we got like a minute or two. Right. So it's nice to see the theory, but let's see the numbers. So for this particular problem, if f of x y equal to 9 minus x or minus y squared, then the gradient of f is equal to, well, the partial with respect to x is negative 2x. The partial with respect to y is negative 2y. The gradient of f at the point of interest, which is the point 1, 2, right? That's what we were looking at when x was 1 and y was 2, is going to be the vector negative 2, negative 4. So then the directional derivative is going to be that gradient, negative 2, negative 4, dotted with the direction vector, which is 4/5, 3/5. Taking the dot product, we get negative 2 times 4/5, which is negative 8/5, plus negative 4 times 3/5, which is negative 12/5, which I guess I could have written. So we end up with negative 8 plus negative 12, which is negative 20/5, which is negative 4. So what we are saying is that on, I want you to see this. So I'm gonna, yeah. Sure. On this surface, sorry, I'm covering things up, I know. On this surface, if you travel outwards, you end up going down at a steepness of a slope of negative 4, meaning every unit you travel outwards, you're going to travel 4 units downwards. Okay, so the last thing I'll say here, just real quick, is I picked this vector kind of with care. If you'll notice, or maybe not, the vector 4/5, 3/5 has a magnitude of 1 or a length of 1. And when you're finding a directional derivative, this vector here actually does need to have a length of 1. So if you have a vector that isn't a length of 1, you divide by its own magnitude to make it a length of 1. We'll talk more about that next time, but that's kind of the idea, is that, and I'm just going to say, so here's the very last thing. Generally, we write this using a u. We're going to say the directional derivative of f in the direction of u is equal to the gradient of f dotted with the vector u, where u is a unit vector, meaning a vector of length 1. So if you're given a vector that doesn't have length 1, you can say, oh, well, if we're given v, you find u by taking v divided by its own magnitude. It's a very easy way to get a unit vector. Actually, not just an easy way, it's the only way to get a unit vector in the direction of your original vector. All right. I think we're good. We stop. It's 3:01. I have office hours over in CADS. I will be there as soon as my feet will get me there. Well,